In this section, I want to look at Pythagorean triples. So these are integers that would form the three sides of a right triangle. And I want to look at the more general question of finding rational points on any type of conic section. So first we'll define what a primitive Pythagorean triple is. And then we're going to come up with a way of describing all Pythagorean triples. Then I want to note the connection between finding integer solutions of a homogeneous quadratic and finding rational points on a conic section. And in doing this, we're going to describe a general method for finding all rational points on any conic section given one point. And then finally, we'll just state Legendre's theorem, which gives us a criterion for determining when a conic actually contains some rational point. Although I'm not going to do the proof in this section, we'll do the proof in one of the later chapters in the notes. So Pythagorean triples, you've all seen these growing up. There are triples like 3, 4, 5, or 5, 12, 13, or 8, 15, 17. There are whole numbers that form the three sides of a right triangle. So 3, 4, 5 is probably the most popular one. Or 5 like this. And another popular one is 5, 12, 13. And 8, 15, 17. So here we've got 3 squared plus 4 squared is 5 squared. 5 squared is 25 plus 144 is 169. And then the final one I've put as an example is 8, 15, 17. 64 plus 225 is 289, which is 17 squared. So a Pythagorean triple is called primitive if the GCD of the three numbers equals 1. And note, every Pythagorean triple is just a multiple of a primitive one. So for instance, I could double these three sides and I could come up with 6, 8, 10. That's another very popular Pythagorean triple. 36 plus 64 is 100. But we're not interested in finding these. These type of Pythagorean triples are obtained as multiples of the primitive ones. So our goal is just to classify all primitive Pythagorean triples. Now the way we're going to go about finding the Pythagorean triples is to connect the problem with a related question about finding rational points on a circle. So let's suppose we have a triple UVW satisfying u squared plus v squared is w squared. Divide both sides by w squared. And I get u over w squared plus v over w squared equals 1. Well, that means that the point u over w, v over w is a rational point on the unit circle x squared plus y squared equals 1. So here's the circle. X squared plus y squared equals 1. And on this circle, I've got a point, both of whose coordinates are rational, u over w comma v over w. So we can also note that if the Pythagorean triple is a primitive one, then the fractions I've obtained are in fact in reduced form. And so the goal of finding the Pythagorean triples becomes related to the question of finding rational points on this circle. So we're going to start by trying to find all rational points on the unit circle. Okay, so I've drawn the unit circle here, and I've drawn a line going through the point -1, 0, call that point B, and it will intersect the circle at some point C right here. So let's say that this line has slope m. So let LM be line passing through the given point negative 1, 0, and having a rational slope m. So m I'm going to take to be a rational number. Okay, what's the equation of this line? So we have y minus y1, which is 0, equals m times x minus negative 1. So I'm using the point B as the given point. So it's y equals m times x plus 1. And let's intersect the line with the circle. So I just plug this in. We have x squared plus y squared equals 1. So x squared plus mx plus 1 squared equals 1. Multiply this out. And now, rather than just do brute force here, let's try to be a little bit clever. This is going to be a quadratic equation. And we know that negative 1 is one of the solutions, which means that x plus 1 is going to be a factor. So note x plus 1 is a factor since negative 1 is a 0. Therefore, I'm going to try to factor out an x plus 1, and I can see how to do that. I'm going to put the x squared over to the right, like this, and then I'll factor 1 minus x squared. And that pulls off that x plus 1 factor, which I then cancel. At this point, I'm assuming x plus 1 doesn't equal 0. I'm not interested in finding the point B. We're trying to find the point C up here. And we get m squared x plus m squared times 1 equals 1 minus x. And we're trying to solve for x, and that's just a linear equation. X times m squared plus 1 is 1 minus m squared, which gives us x to be 1 minus m squared over 1 plus m squared. And then given x, we can find y, m times x plus 1, like that, which is m times 1 minus m squared plus 1 plus m squared, which is just 2 over 1 plus m squared, and we get 2m over 1 plus m squared. And that's the second point of intersection. So, we've seen that every rational point on this circle is of this form. X is 1 minus m squared over 1 plus m squared, and y is 2m over 1 plus m squared, where m runs through the rational numbers. And then, of course, we have to throw in the point negative 1, 0 as well. Now, how did I know that this gives us all of the solutions? Why is this all solutions? In other words, why is every solution obtained by that intersection method? Well, say we had a rational point on the circle. Okay, so if you have a given rational point on the circle, draw a straight line connecting that rational point to our given point, negative 1, 0. And the slope of that line must therefore be a rational number. So it must have been one of the points we've already accounted for. Okay, next. If m is a rational number, we can write it in the form a over b with a and b relatively prime. And so just doing that and plugging it in here, we get that x is this big stacked fraction, which simplifies to b squared minus a squared over b squared plus a squared. And y plug it into the 2m equation, is 2a over b, and get the common denominator here, and then flip this, cancel out one of the b's, and we get 2ab over a squared plus b squared. So this is another way of describing the rational points using integers a and b. Okay, now let's return to the Pythagorean triples. So suppose u, v, and w is a positive primitive solution of our Pythagorean triple equation. So u squared plus v squared is w squared. Now first note that if this is a primitive solution, then in fact u, v, and w are pairwise relatively prime. Because if any two of these numbers, say u and v, shared a common prime factor p, that would say that p squared is a divisor of the left-hand side, and therefore p squared would be a divisor of the right-hand side, and that would imply that p is a divisor of all three numbers. But our assumption is that there is no common divisor of all three numbers. Note also that the values u and v have opposite parity. So one of them is even and one is odd. And why is that? Well, they are pairwise relatively prime, so they can't both be even. Both be even, since u and v equals 1. And why can't they both be odd? Well, if u and v are both odd, then I come back up to this equation and I look at u squared plus v squared. Well, that would be congruent to 1 plus 1, which is 2 mod 4. But we've seen before that 2 is not a perfect square mod 4. So we can't have this 2 come out to be a w squared. Okay, so therefore one of them is even and one is odd, and so we'll go ahead and assume that u is the odd number and that v is the even number. And then dividing both sides of this equation by w squared, we see that u over w, v over w is a rational point on the unit circle in reduced form. And on our previous slide, we just characterized what every rational point looks like on the unit circle. So what do we get? So u over w has to have this form, and v over w has to have this form for some positive relatively prime integers a and b. Now what I want to claim is that these are all reduced fractions. So u over w and v over w are reduced by our previous definition. So why are these ab fractions in reduced form? So that's a claim. And then once we prove that claim, it will follow by the uniqueness of representations of reduced fractions, and this was a homework problem you did earlier, that the tops match and the bottoms match. So u would be b squared minus a squared, w is b squared plus a squared, and v would be 2ab. All right, let's prove the claim. So we've made the assumption that u is odd, v is even, and therefore w is also odd. See if we may not need that fact. So I want to first show that a and b have opposite parity. So one of them is even and one of them is odd. So why is that? So we're assuming that a and b are relatively prime. Well, if I come back to this equation right here, up on top, that gives us u times a squared plus b squared is w times b squared minus a squared. And if I look at this mod 4, I claim we're going to have a problem. If A and B have the same parity. So if A and B are both odd numbers. So if A and B are both odd, then A squared plus B squared would be congruent to 2 mod 4. And U is an odd value, so that's congruent to 1 or 3. And this would be times 2. Should be congruent. W is an odd number, so that's a 1 or 3. And B squared minus A squared, if A and B are both odd, that would be 1 minus 1, which is 0 mod 4. So the left-hand side is 2 mod 4, and the right-hand side is 0, which is a contradiction. Therefore, we can't have A and B both being odd. Okay, now let's calculate the GCDs of these fractions up here. This one and this one. We claim these are reduced fractions. So if I look at b squared plus a squared comma b squared minus a squared, the first step, what did I do? I just multiplied this entry by -1 and added to the second entry to get -2a squared. Then I realized that this number here is odd, and therefore this 2 plays no role in the greatest common factor, and I can just delete it in this step. And then I subtract the a squared entry from this to cancel that guy. And then I realize that b and a are relatively prime, and I get 1. Likewise, b squared plus a squared comma 2ab, I say, well, that's an odd number, so I can ignore the 2. And then you had a homework problem that said if these are relatively prime, I can break it up as the first number times with a times the GCD of the first number with b, and then I subtract a multiple of a to get rid of that. I subtract a multiple of b to get rid of this, and we get b squared a squared b, and again a and b are relatively prime, so that comes out to be 1. Good. So we have up in equation 1 reduced fractions on both sides, and so that completes the characterization of u, w, and v. So theorem. The set of positive primitive solutions of the Pythagorean equation u squared plus v squared equals w squared with v even and u odd is given by u equals b squared minus a squared, v equals 2 times ab, w equals a squared plus b squared, where a is less than b in all positive numbers, a and b are relatively prime, and a and b have opposite parity. And then you can just enumerate all such possibilities. So in this table, I'm just writing down all pairs with a and b relatively prime having opposite parity. So 1, 2, and that'll generate the 3, 4, 5. If I plug in 2, 3, I get 5, 12, 13. 1, 4 gives us the 15, 8, 17. So those are the 3 we started with. And now we'll start getting some new triples. When a is 3 and b is 4, I get a 7, 24, 25, and so on. So you might look through that table and see if you see any interesting patterns or want to make any conjectures about the type of triples you end up with. But one point we can make is that there are infinitely many Pythagorean triples, infinitely many primitive Pythagorean triples. Okay, now let's generalize the problem. So let's let q of xy be any quadratic polynomial with rational coefficients. So second degree polynomial where a, b, c, d, e, and f are rational numbers. Then we get a conic by just setting this equal to 0. and I want to find all rational points on this conic, starting from a given rational point. So when we did the Pythagorean triples, I drew the circle, and I said, there's a starting point, -1, 0. So let's suppose we have a starting point for this conic, a given rational point. And I'll come back and discuss when a conic can have a rational point. And then note also that solving for the rational points in the conic is equivalent to finding integer solutions of this homogeneous equation. The ax squared bxy cy squared dxz plus eyz plus fz squared equals 0. All right, here's a couple homework problems where you do problems of this type. In the first one, I want to find all rational points on the ellipse, x squared plus 5y squared equals 1, and that would correspond to finding all integer triples, u, v, and w. They're not going to be Pythagorean triples, but they satisfy u squared plus 5v squared equals w squared. Or another problem. Find all triangles with integer side lengths having a 60-degree angle. And you'll show that that's equivalent to finding all solutions of an equation like this. U squared plus v squared minus uv equals w squared. Dividing both sides by w squared, we see that's equivalent to finding rational points on this conic right here. So what's the procedure then in general? So we suppose x0, y0 is a given rational point, and what I do is I draw a line. So if you imagine it being like an ellipse here, here's my given point x0, y0, and I just draw a line through that point of slope m, so I let y equal mx plus b be aligned with a rational slope m passing through the given point x0, y0, and I just find the second point of intersection. So I insert the equation of the line right here, and this gives us a quadratic equation in a single variable x. And then I can use the fact that x0 is a given solution, and so it's very easy to find the second solution of the quadratic. And in fact, the second solution must also be rational because the first solution is rational. And then step 3 is just to note that you really have accounted for every rational point on your conic section up here. And that's all there is to it. Now, as to the existence of this first rational point, this is a much more difficult question. So what we do is we first simplify the conic. So you complete the square, clear denominators if necessary, and any common factors, and you put it into a very simple form like this. ax squared plus by squared equals c, where a, b, and c are pairwise relatively prime integers and c is positive. And so finding a rational point on this equation right here is equivalent to solving this homogeneous equation for integers. So au squared plus bv squared equals c w squared. Now, a necessary condition for solving this is that we have a real solution. And since I've specified that c is positive, at least one of these two values, a or b, must be positive. So that's the first constraint we're going to need to have a chance of being solvable. Another necessary condition for solvability of this equation in integers is that each of the following congruences is solvable. So I take the equation and I just view it mod c to get au squared plus bv squared is congruent to 0 mod c. And then mod a, it looks like bv squared is congruent to cw squared, and mod b, it's au squared is congruent to cw squared. So in order to have a chance of having an integer solution, each of these congruences must be solvable. So we've got 4 necessary conditions. The fact that either A or B has to be positive, and these 3 congruence conditions. And the remarkable theorem that Legendre proved is that these 4 necessary conditions really are sufficient. So he proved a theorem that says, roughly speaking, the following: if the 4 necessary conditions listed above are all satisfied, then there exists an integer solution to the equation au squared plus bv squared equals cw squared. We will in fact state the theorem and prove it more precisely later on in the chapter on the geometry of numbers. But for now I just want to point out that this theorem gives us a condition on when a conic section is going to contain at least one rational point.